Hello and welcome. In this video, I want to take a look at examples of vector fields. And just because of the difficulty of drawing and visualizing them in R3, I'm going to stick with just vector fields in R2 for this video. I'm using an online um, vector field grapher that's powered by GeoGebra. The link is in the course page. So I'm just going to start with just going to go through a bunch of different examples here and see some things. My first one is the vector field xy is equal to minus x minus y. So at each point, I'm thinking of the vector which points directly back at the origin. Now, again, I have it drawn not to scale, because if this was drawn to scale, I put this v up to 1 here, every point would be just long enough to get right exactly back to the origin, and it becomes not as helpful to see what it looks like. So we scale everything down here to draw a little bit smaller vectors at each point. But you still get the sense that the vectors are bigger further away here and shorter closer down in to the origin. But they're all pointed towards the origin. This happens to be a vector field that you would have seen back in Calc 3 because it is a gradient field. That if you think about the function, or actually it's the vector field, it's the gradient field for an upside down paraboloid. So z equals the quantity x squared plus y squared all over 2, right? All over negative 2 because it's an upside down one, right? So the first component here, if I think of that, think of it as negative x squared over 2 minus y squared over 2. So the partial with respect to x would be the negative x, and the partial with respect to y would be the negative y. So this is indeed the gradient of that function. Okay. Next example is very similar, but I just want to scale all of these vectors to have the same length. So what I've done is I've divided the negative x by x squared plus y squared, the negative y by the square root of x squared plus y squared, because the vector that I had before, the negative x comma negative y, the length of that was, of course, the square root of x squared plus y squared. So now I've got a vector field that, again, is still, everything's pointing at the origin, but this time all the vectors are the same length. Okay. Is this a gradient field? It turns out it is. It's the gradient field for an upside down, well, an upside down cone. So it would be like z equals minus the square root of x squared plus y squared, and I'll say probably need that over 2, but I don't think you do. So z equals minus the square root of x squared plus y squared. Would be the function whose gradient is this, and it's producing this vector field. If I were to divide by that square root of x squared plus y squared again, I get a vector field that is looking more like it's a gravity field, like the force of gravity. And this is one thing that I want to point out as well. I say the force of gravity. We use vectors to signify a lot of things like velocity or acceleration or force. And some of these vector fields I view as a velocity field. It's like water flowing across the thing, and it's telling me where the water is going and how fast the water is going at any point. Or in other times, I think of it as an acceleration field or a force field, where the vectors are telling you the direction and magnitude of the acceleration on a particle that would be there. Gravity, for instance, is a force. Maybe it's an electromagnetic field that you're looking at, which is generally a force field. Okay, this is not a gravity field. It is very similar to one. Right? You can see it's like there's an object right here that things are being pulled into, and the closer you are, the stronger the pull. However, gravity generally works on the force of the gravity is proportional to the to the reciprocal of the square of the distance, right? Inversely proportional to the square of the distance, where this is actually just inversely proportional to the distance. So I need to multiply, or I need to divide everything by that square root of x squared plus y squared again. And now I've got it, the square root cubed, so it's raised to the 3/2 power down there. And this would be a gravity field pulling towards this point here with the force inversely proportional to the square of the distance. Is this also a gradient field of some potential function? I haven't used the word potential function before now, but we will talk more about potential functions in the next video. And the answer is yes, although it's not immediately obvious. I then went on to do this example where I said, oh, could I have like two gravity sources and maybe of different strength? So there's a gravity well right here that things are being pulled to of strength 2 and something right here of strength 1. So you can see there's places in the middle, right? Something along here, well, maybe in, you know, where do things get pulled one way or the other, right? Stuff is being pulled in here. The vectors are a little bit too long here when you get too close to those points, so I can scale them down to see a little better what's going on. But yeah, there's a transition of when do you get pulled in this way or when do you get pulled in that way. Because this one's stronger, the transition is closer to the weaker one, where this has a bigger gravitational well, so to speak. Yeah, there's all kinds of things that you can do and create, you know, multiple sources of gravity and add them up. You can't really see what my formula is here because it's rather long. I can go through it here that the gravity to begin with here, this first one with the minus x plus 2 is this one right here, and it's being divided by that x squared, well, x minus 2 squared plus y squared to the 3/2 power. So that's the inverse of the square property for that one, and then I'm adding to it, or in this case subtracting to it because it's being pulled towards it anyway, the 2 times the gravity that would be headed towards this one. And so this has that at the -2, and a similar thing happening with the y's. Okay. I find it fascinating to be able to just write down these formulas for doing gravity at different places. You could then think about modeling, putting an object in there and watching a path that it might have, give it some initial velocity and see where it would go. Just fun stuff. Let's take a look at another example here. When you first just find the link to this GeoGebra vector field plotter, this is the default that comes up. And this looks very much to me like the sort of magnetic lines that you've got a magnet here with a North Pole and a South Pole, or the other way around, and that these magnetic flux lines are moving or going from one to the other. I don't think that it is. I don't know for certain. But the thing I notice about it is that as you get close to the poles, the vectors get shorter, and the further away, the bigger the vectors are. I would expect that this would be the opposite if this was actually essentially the force field generated by a magnet, or maybe 2 electric charges. Let's put a positive charge here and a negative charge there, and then stick an electron out here somewhere, and it's going to be pushed away from the negative charge and towards the positive charge. But it would be bigger pushes or bigger pulls when you're close to those 2 sources, rather than the opposite is showing here. So somehow we could manipulate this and maybe change the lengths to do what we want. I've not going to do that right now, but at least we got the right sort of shape for something like that. Let's see, another example here. Oh, this one's a fun one. This is just the point xy is being assigned the vector y negative x. And it looks like you've got a bunch of circular motion here. Again, this one I don't see so much as acceleration, but I see it as velocity. In fact, if you take a flat thing and rotate it around some center, right, and it's a rigid thing, the stuff on the outside has to be moving around, has to be moving faster than the stuff on the inside, because they'll make one cycle in the same amount of time, but the outside one travels a much bigger distance than the inside one. And so this would be a velocity field for such a situation, right? Rotating around the origin. As I move outward, you have to have greater speed in order to keep up with the stuff that doesn't have to move as far. Right? If you've ever been roller skating or ice skating, you know, and you make that chain of people and you do the whip, right? That one person on the outside gets whipped around really fast because you're all trying to stay in a line, and the outside person has to go substantially faster than the inside person. You might think about how you would change this to get them all the same length. Or maybe change it so that, you know, if you're thinking about a whirlpool, right? If you look at a whirlpool of water, it's usually moving slow on the outside and it's moving fast on the inside. Or a tornado, right? Of course, a tornado is just a whirlpool of air. And it's moving very fast around that center and very slow around the sides. And so it's like, well, how would I change this vector field in order to accomplish that? I think I can just, like I will do it right here. I can do it by dividing by, I'm going to divide by the length squared. Again, this one, if I take the length of this vector, it's going to be the square root of x squared plus y squared. So I'm just going to divide by x squared plus y squared. If I throw a square root in there, I'm dividing by its own length, and everything will have length 1. So I'm dividing by the length squared here. It looks a little funny to start with because I've adjusted the x, but I haven't adjusted the y, and I didn't even adjust the x the way I wanted to. It's something like this. I got to go back and do that again. X squared plus y squared squared. There we go. Likes that. Okay. And what happened here? This should have been x squared plus y squared. Yeah, there we go. That looks a little better. Ah, yes. So I can see now that my vectors down in the middle are substantially longer than the ones on the outside. So this is more like a whirlpool or a tornado, where you're moving slowly on the outside and you're moving very fast on the inside. Another example. This one I just like. This is one you would have seen back in Calc 3 as the gradient of the hyperbolic paraboloid. It is x squared minus y squared all divided by 2. X squared minus y squared all divided by 2. If you think about what's the partial with respect to x, it would be 2x. That's the first component. What's the partial with respect to y? Well, the minus y squared gives you the minus 2y for the partial with respect to y, and that's this component here. So this is, in fact, a gradient of the function x squared minus y squared. But it's a vector field. It's a vector field. And I see this as, you know, because I've seen it first as a gradient field, I think about it in terms of the vectors pointing uphill, right? Because that's what, well, they don't point uphill, they point in the direction where it's the steepest uphill. So I see a surface here which is telling me, you know, it's up on this side because the vectors are all pointing here. It's down low and it's down low here because the vectors are all pointing away from those places, and again it's up there. So this is a saddle that's, you know, bending downward in the y direction and bending upward in the x direction. Gradient field, which we've seen before is a vector field. And one last one here. I threw this one up here just because I mentioned it in the last video that our conversion from xy to polar coordinates is, in a sense, a vector field. The difference is when we convert r's and thetas to x's and y's, we use different variables for the input variables and the output variables. Where here in um, talking about vector fields, we generally think of the same one, that xy gets sent to some other xy, and we interpret that as a vector, right? So what I'm doing here is I'm saying that I want a vector field where the x component is x cos y and the y component is x sine y. So I'm thinking of the input variable y as I used to think of theta, and I'm thinking of the input variable x as I used to think of r. And then I'm just plotting that right on the spot where it came from. Right? And what I see is I see these different vectors do different things. Notice as just pick one and move just in the x direction. What's happening is the vectors seem to go parallel to each other, but getting longer. Well, x is playing the role of r. So as x is getting bigger, those vectors are getting longer. Likewise, if I pick just a particular value of x here and change y, I see a vector that's, horizontal, pointing in the positive x direction, and it's tipped up a little bit, and it's tipped up more, and then it's tipped up more, and tipped back, and now it's pointed in the opposite direction, and then rotates around. That is, as I move in the y direction, my vectors seem to be just rotating. Well, y is playing the role of theta. So this vector field is essentially the same as the polar coordinate conversion. Rather than saying xy equals r cos theta and r sine theta, I'm saying that this output, this vector that I'm getting as an output, has x cos y, x sine y as its two components. Okay. Yeah, there's polar coordinates. You might think about if you could draw, pull up a 3D one and look at spherical coordinates as a vector field. Right? Take one of your variables as rho and one of your variables as theta and one of them as phi, and plot the vector field based on the spherical coordinates formulas. So anyway, there you go. There's a bunch of examples.